Welcome back to Bite-Sized Breakthroughs, the podcast exploring the latest and greatest advancements in the world of technology. Today, we're diving into a fascinating research paper that tackles a core challenge in large-scale recommendation systems, the efficient retrieval of relevant items. Joining us is Dr. Paige Turner, the lead researcher on this project, and Prof. Wood Spectrum, a renowned expert in the field of recommendation systems. Welcome, both of you.
Thank you, Alex. It's great to be here.
My pleasure to be here, Alex.
Paige, let's start with the basics. What's the central problem this paper addresses, and why is it so significant?
Sure, Alex. The paper focuses on the challenge of efficiently retrieving relevant items in large-scale recommendation systems. Imagine platforms like YouTube, Amazon, or TikTok, where users are presented with a vast library of content. The key is to identify the most relevant items for each user based on their preferences and past interactions. But when you're dealing with millions or even hundreds of millions of items, the task becomes incredibly complex.
And that's where the issue of scalability arises. How do you find the needle in the haystack without taking forever?
Exactly. Traditional approaches often involve two steps. First, they learn a vector representation for users and items, capturing their relationships. Then, they use approximate nearest neighbor search algorithms, like those based on trees, hashing, or product quantization. These algorithms aim to find similar items in a computationally efficient manner.
So what's wrong with that approach? It seems to make sense.
While these approaches have been successful, they have limitations. First, the inner product structure of these vector-based models may not fully capture the complex nature of user-item interactions. Think of it like trying to describe a symphony using only notes. It misses the nuance and complexity. Second, these algorithms approximate the learned model instead of directly optimizing for user preferences. It's like taking a shortcut, but you might miss the best possible path.
That makes sense. So what's the proposed solution?
The paper introduces a novel approach called Deep Retrieval, DR. Instead of relying on vector representations, DR learns a retrievable structure directly from user-item interaction data. Think of it as a map with different paths representing distinct clusters of items based on user behavior. Each item can be assigned to multiple paths, reflecting its multifaceted nature. This allows us to capture complex relationships between users and items more effectively.
Okay, so instead of using vectors and approximating, DR creates a more intricate map of user preferences. But how does this actually work in practice?
Good question, Alex. Let me break it down. DR uses a matrix with K nodes in each layer and D layers. Each item is assigned a unique path traversing this matrix, indicating its cluster memberships. The model learns the probability of each path given user input, effectively capturing how likely a user is to interact with items within that cluster. During inference, a beam search algorithm efficiently explores the most probable paths, retrieving top candidates for further ranking.
It sounds like DR goes beyond simply retrieving similar items. It's actually learning a structure of user preferences. Wid, from your perspective, how significant is this shift in approach?
That's exactly right, Alex. This paper presents a paradigm shift in recommendation systems. Traditionally, we've focused on finding similar items based on their vector representations. DR, however, takes a more nuanced approach by learning a structure that directly reflects user-item interactions. This is a huge step forward in capturing the complexities of real-world preferences.
Paige, can you elaborate on how this multipath mechanism works and how it benefits the system?
Certainly. The multipath mechanism is key to DR's effectiveness. It allows us to assign each item to multiple paths, representing its multifaceted nature. For instance, a chocolate cake could be relevant to both food and gift categories, appealing to users interested in either. This design helps to overcome the limitations of traditional tree-based models, where each item is confined to a single leaf node. This can lead to data scarcity at finer levels of the tree, especially with large data sets. DR's multipath design mitigates this problem, allowing items to be associated with diverse clusters and capturing a wider range of user preferences.
That's a great illustration, Paige. But how does the model actually learn this structure? What's the training process like?
DR utilizes an expectation maximization (EM) style algorithm for training. It iteratively updates the model parameters and the item-to-path mappings. The E step optimizes the model parameters for a fixed mapping, while the M step updates the mapping based on the optimized parameters. This process is designed to maximize the likelihood of observed user-item interactions, ensuring that the learned structure reflects user preferences as accurately as possible.
That's fascinating. It seems like DR goes beyond traditional machine learning approaches by directly learning the structure of the data. Wid, can you comment on the significance of this aspect?
Absolutely, Alex. This is where DR truly shines. Instead of relying on predefined structures or fixed representations, it learns a structure tailored to the specific data at hand. This makes it particularly well suited for large-scale recommendations where user preferences are diverse and constantly evolving. This ability to adapt to the specific characteristics of the data gives DR a significant advantage over traditional methods.
Paige, let's move on to the experimental results. What data sets were used to evaluate DR, and what metrics were used to measure its performance?
We evaluated DR on two publicly available datasets, MovieLens 20M, containing movie ratings and tags, and Amazon Books, featuring user reviews of books. We compared its performance with several baseline methods, including ItemCF, YouTube DNN, TDM, Tree-Based Deep Model, and JTM, Joint Tree Model. We also included a brute force retrieval algorithm as an upper bound for inner product-based methods. Our metrics included precision, recall, and F measure at different cutoff points. These metrics capture the accuracy and completeness of the retrieved item sets.
Okay, so you had a comprehensive set of baselines and metrics. What were the key findings? Did DR outperform the other methods?
Absolutely. DR consistently outperformed the other methods on both datasets, achieving near brute force accuracy. For example, on the MovieLens 20M dataset, DR achieved a precision at 10 of 20.58%, recall at 10 of 10.89%, and F measure at 10 of 12.32%, which is very close to the brute force results. Similarly, on the Amazon Books dataset, DR achieved a precision 200 of 0.95%, recall at 200 of 13.74%, and F measure at 200 of 1.63%, again, closely matching the brute force performance. This demonstrates that DR can achieve comparable accuracy to the computationally expensive brute force approach, while being significantly more efficient.
So DR achieves similar accuracy but with less computational overhead. How much faster is it compared to brute force?
In our experiments, DR was significantly faster than the brute force approach. On the Amazon Books dataset, DR's inference time was about 4 times faster than the brute force method. This makes a huge difference in real-world applications, where performance is critical, especially with large datasets.
That's a significant improvement, Paige. Wid, from your perspective, how important is this speed up in the context of real-world recommendations?
It's absolutely crucial, Alex. In real-world scenarios, recommendation systems need to be lightning fast. Users expect instant responses and personalized recommendations. DR's efficiency allows it to scale effectively to handle the massive datasets and high demand of modern platforms. This speed-up is essential for delivering a seamless and satisfying user experience.
That makes a lot of sense. Paige, you mentioned that you also tested DR in a live production environment. Can you tell us about that experiment and its outcomes?
Yes, we deployed DR in a live recommendation system with hundreds of millions of users and items. We compared it with a well-tuned baseline system using field-aware factorization machine, FFM, and HNSW for candidate generation. DR was used as a candidate generation component, producing a set of items for further ranking by a logistic regression model. We observed significant improvements in key engagement metrics, including video finish rate, app view time, and second-day retention. DR led to a 3% increase in video finish rate, a 0.87% increase in app view time, and a 0.036% increase in second-day retention, all statistically significant. This clearly demonstrates that DR not only improves efficiency, but also leads to more engaging and successful user experiences.
That's impressive. Wid, can you offer some insights into why DR might be leading to these improvements in user engagement?
It's likely due to the end-to-end learning of DR, Alex. By jointly optimizing the model parameters and item-to-path mappings, DR ensures that the learned structure directly reflects user preferences. This leads to more accurate and relevant recommendations, which in turn translates to increased engagement. Additionally, DR's ability to represent multifaceted information through multiple paths might contribute to a more diverse and inclusive recommendation experience, potentially leading to higher user satisfaction.
Paige, you mentioned that DR was particularly beneficial for less popular videos and creators. Can you shed light on why that might be the case?
Yes, we observed that DR effectively promoted less popular content. This is likely because within each path, all items are considered equally, allowing less popular items to be retrieved as long as they share similar behavior patterns with popular ones. This effectively helps to diversify the recommendation pool and provide more exposure to content that might otherwise be overlooked.
That's a very important point, Paige. It highlights the potential of DR to contribute to a more diverse and equitable content ecosystem. Wid, from your perspective, how significant is this aspect in the context of recommendation systems?
It's absolutely critical, Alex. Recommendation systems often suffer from filter bubbles, where users are only exposed to content that confirms their existing biases. This can limit their discovery of new ideas and perspectives. DR's ability to promote less popular content helps to mitigate this issue, fostering a more inclusive and diverse online environment. This is essential for promoting healthy content ecosystems and ensuring that all voices have a chance to be heard.
Paige, are there any limitations or challenges associated with DR that you'd like to discuss?
Of course, Alex, while DR offers significant advantages, it does have some limitations. Firstly, the current structure model primarily relies on user-side information. Integrating item-side information directly into the model could potentially enhance its performance and accuracy. Secondly, DR currently only utilizes positive user-item interactions. Incorporating negative interactions, such as dislikes or non-clicks, could provide a more complete picture of user preferences and potentially lead to improved recommendations. Finally, the re-ranker used in the live experiment was a simple logistic regression model. Exploring more complex re-ranker models could further enhance the accuracy and effectiveness of DR-based recommendation systems.
It's good to acknowledge those limitations, Paige. Weed, any thoughts on the potential impact of addressing those challenges in future research?
Addressing those limitations would make DR even more powerful, Alex. Integrating item-side information would allow for a more comprehensive understanding of the items themselves, leading to more accurate and relevant recommendations. Incorporating negative interactions would provide a more nuanced view of user preferences, potentially uncovering hidden patterns and improving the recommendation system's ability to avoid presenting content that users dislike. Finally, exploring more advanced re-ranker models could lead to more sophisticated ranking algorithms, potentially enhancing the overall quality of recommendations and providing users with a more personalized experience.
Paige, what are some potential future research directions based on this work?
There are several promising avenues for future research, Alex. One exciting area is exploring different ways to incorporate item-side information into the DR structure model. This could involve using features like text descriptions, image data, or metadata associated with each item. Another area of focus could be developing techniques to effectively utilize negative interactions in the learning process. This would provide a more comprehensive understanding of user preferences and potentially lead to more robust and accurate recommendations. Finally, we could investigate the use of more advanced and complex re-ranker models, potentially leveraging techniques from deep learning or reinforcement learning to further enhance the ranking of retrieved items.
Those are all exciting possibilities, Paige. Wid, what's your take on the broader impact of this work and its potential applications?
I believe this paper has the potential to significantly impact the field of recommendation systems, Alex. It provides a powerful new approach that can handle the challenges of large-scale datasets and dynamic content. DR's efficiency and accuracy make it a compelling solution for a wide range of applications, including product recommendations, article recommendations, music recommendations, and even personalized search. The concepts explored in this paper, such as discrete latent space representations and path-based structures, could also have implications for other machine learning domains, such as image retrieval and document classification. This work could potentially lead to a shift in the way we think about representation learning and model design in machine learning, paving the way for more efficient and effective solutions to complex problems.
That's a fantastic overview, Wide. Paige, any final thoughts you'd like to share with our listeners?
It's been a pleasure discussing this research with you both, Alex. I believe DR represents a significant step forward in the field of large-scale recommendation systems. It effectively addresses the limitations of traditional approaches and demonstrates its ability to deliver highly accurate and engaging recommendations with exceptional efficiency. The future of recommendation systems is incredibly exciting, and I'm confident that research like this will continue to push the boundaries of what's possible.
Thank you both for joining us and sharing your insights. This has been a truly illuminating discussion. Listeners, if you're interested in learning more about deep retrieval and its potential impact, be sure to check out the research paper linked in our show notes. Until next time, stay curious and keep exploring the world of technology.